Hey everybody. Today we're going to be talking a little bit about organic chemistry. Okay, so organic chemistry is kind of a focus on carbon chemistry. Carbon's a really versatile element that can make all kinds of molecules just because of the tendency for it to make four bonds. It can chain to itself almost infinitely and create branched chains. And then, of course, you can have other stuff attached to those chains. And so you can get some really complicated molecules that are related to life and life functions. I think that's kind of where the term organic comes from. Here are some examples of where you're going to see organic molecules in everyday life and some uses of organic molecules and things like that. I'm not going to go through those individually right now, but you can see, organic chemistry is a broad topic. People go to school for a long time and focus just on polymer chemistry, or something like that. Or just on synthetic pharmaceutical chemistry in a very very narrow track that you need to know a lot about. But we're going to kind of be scratching the surface here, and today we're really going to be focusing on a kind of organic molecules, kind of to get our foot in the door, where we're only looking at carbon and hydrogen. Making molecules. And the first example that I'd like to discuss with you here is butane. You might know butane as lighter fluid. It's the fluid that you would see inside, your standard disposable lighter. It's a liquid under pressure at room temperature, but then, when you open up the valve on a lighter, it turns into a gas. So it converts, between a liquid and a gas just with pressure, slight pressure changes there. But this is a fairly simple organic molecule as organic molecules go. And you can see here C4H10, it's got 4 carbons and 10 hydrogens. So this has got 14 atoms in it, and this is a simple organic molecule. So this kind of tells you, where we're going here. Okay, so if you wanted to know what the structure of this thing looks like in terms of a Lewis structure, it's pretty simple. You've got 4 carbons that are all attached to each other. Now remember, every carbon needs to follow the octet rule here, and so this carbon on the end could attach to 3 hydrogens. This carbon in the middle of other carbons is already connected to 2, so it can connect to 2 other hydrogens. And same here. And then over here on the end, this carbon could connect to 3 other hydrogens. And if you count up all the hydrogens I've got here, you'll see that there's 10, kind of 4 on the top, 4 on the bottom. That's 8, and then the 2 extras on the ends. Now, if you are writing a big molecule, sometimes organic chemists don't like to write the entire structure here. They like to use something like a condensed structure. So condensed structures, we'll put the number of H's attached to each carbon right after them and use some subscripts. So the structure might look something like this. CH3 for this carbon is attached to CH2, that's this one, is attached to CH2 here, and finally back to CH3. Now you can imagine if this chain got very much longer, you'd have a whole bunch of CH2s in the middle. And one way that you can kind of shorten that down is, if you've just got a bunch of CH2s in the middle there, you could do CH3 attached to, in parentheses, CH2, 2, and then back to CH3, and the 2 CH2s in the middle could be condensed even further into this right here, saying, okay, we got 2 of them connected end to end there. Now, even this, though, is a little busy, I think, for a lot of organic chemists. They prefer something called a line structure or a line angle formula. Now, if you were to look kind of, at VSEPR theory, all these angles would be 109.5 degrees. And so, even though this Lewis structure shows all these carbons straight across, actually they're more like in a zigzag. And so the line structure would show kind of the skeleton of carbons here. And here's the line structure. It's really complicated, okay? Don't blink, you'll miss it. That's it. That's the line structure for butane. And the way that I know that this is butane is there are 4 carbons. There's carbons at every end, and there's carbons at every bend. Okay, it only shows the bonds between carbon atoms. And we didn't write any C's or H's, so you're just assuming that there's a C at every end, there's a C at every bend. Now you could figure out how many H's there are because, okay, this C, is only attached to one other C, so it's got room for 3, and just subtract from 4. This C is connected to 2 others, and so it has 2 spots left over for H's. Same here, and then this one on the end would have 3. Okay, so these are 3 different representations of the molecule butane, C4H10. All right, now butane fits into a category of compounds that we call alkanes. And alkanes are what we call saturated hydrocarbons. And this basically means that they have all single bonds. There are no double bonds in these molecules, and that allows the carbons to hold as many hydrogens as possible. The carbons are saturated with hydrogens. Now, if you look around any single carbon in a alkane, it's going to have 4 single bonds to it. And if you were to use kind of your VSEPR theory and say, okay, we got 4 bonded atoms and no lone pairs around, say, this carbon here or any carbon in the structure, the VSEPR shape is going to be a tetrahedral with 109.5 degree bond angles. Now, there's a general formula for alkanes. Generally, alkanes are going to have a certain number of carbons, and the number of hydrogens is going to be twice that many and 2 more. So the number of hydrogens is twice that many and 2 more. And you can kind of see that back in our butane example here. We had 4 carbons, and the number of hydrogens was twice that many, which would be 8, and 2 more, which would be 10. And if you're got a straight chain hydrocarbon, basically every carbon holds 2, and then the ones on the end hold the extra 2 more. Now, what's interesting is that general formula will work even if a hydrocarbon is branched. The butane that we showed was a straight chain butane. All right, now you do need to learn prefixes for the first 10 straight chain alkanes. This number here is the number of carbons that are in these chains, and the first 4 are the first 4 that have kind of a strange beginning. Methane is CH4 with 1 carbon. Ethane is C2H6. Propane is C3H8, and so on and so forth. I'm just doubling the number of carbons and adding 2 more. Butane that we already saw was C4H10. Those first 4 are a bit hard to remember. Notice everything ends in ane, but it's it's the prefix that you've got to remember here. And my kids came up with a funny little saying just to kind of remember the first letter of these first 4 a few years back that I'll share with you guys. They said, Molly eats peanut butter. Molly eats peanut butter. Helps you remember the first 4 prefixes in order are going to be methane, ethane, propane, and butane. Okay? Now, hydrocarbons can branch. We showed you the case where you had a regular butane, and it looks like this isobutane is actually supposed to be this guy over here. But if you just have a regular butane, the carbons are in a straight line. But you could have the same 4 carbons and maybe them not all be in a straight line. Maybe, pull the carbon off the end and attach it to, say, that middle carbon then. And this is a different molecule, but its formula is still C4H10. Okay, so we got a regular straight chain C4H10, and then we have a branched C4H10. And both of these have the exact same formula, but they are different structures. So when you have the same formula but different structures, we call this structural isomerism. So these 2 are isomers of each other, kind of like isotopes are when you have two atoms of the same element that have different numbers of neutrons. Isomers are two molecules that have the same formula, but different structures. Okay? Now, the more carbons you have, obviously, the more possibilities you're going to have for isomers. And you can see the number of possibilities increases exponentially as you start adding a number of carbons here. Let's take a look at just maybe pentane, for example. I'm not going to draw the hydrogens here, but you can imagine, one isomer of pentane could be if you had, say, 1, 2, 3, 4, 5 carbons attached in a straight line. Now, if you were to, say, bend this chain, it's still the same chain. Okay, so these two are the same. Bending a chain does not make it a different isomer because the chains can bend. Okay. In order to get a different isomer, it's going to have to branch differently. And so instead of all the carbons being in a line, you might have a scenario, say, where one of the carbons was connected to one of the middle carbons. Now, so what if you connected that extra carbon over here to this other carbon? These are the same molecule. You can see, imagine if you took one of those and flipped it over this way, it would look exactly the same as the other one. So attached to a branch at the second carbon, if I was counting from this way, and then if I was counting from this way, it would also be a branch at the second carbon. So these two are the same. These are not different structural isomers, so they have to branch differently. And it's sometimes that's tough to see because if you flip a molecule over and it looks like the same molecule, then it is the same molecule. You didn't actually make a different molecule. Let's see if we can come up with another one here, though. So really the only other way that you could possibly do this would be to pull another carbon off of the end here and maybe make something that looks like this. Okay, so we got 1, 2, 3 possibilities of ways to branch those carbons using 5 carbons, and you can see the number of structural isomers there for pentane is 5. All right, in our next lesson, we're going to get into how to name branched alkanes. Until then.